presentation
is will be recorded and also it will go on YouTube live.
record हो रहा है YouTube
Will
पे भी
stream from 2 p.m. onwards, sir.
Okay.
The sessions are closed only by 1:30 p.m. Maybe participants will join slowly, but anyhow we will start by 2 p.m. sir. Sir, up to few minutes, whether, yes, sir, photo and sir, shall I start, sir?
Okay. Yes, fine with me.
2 more minutes to go.
Yeah, we can start now. After 2 minutes, yeah.
After 2
yes,
minutes.
sir.
Hello, Professor Dinesh Khurana. It's Piyush Chandra here.
Yeah, good afternoon, Professor Chandra. Yeah, nice to
Nice
listen
seeing
to
you, Professor Anumugam also.
Yes, yeah, nice to see him also. Yeah. It's warm there, so everyone is wearing only shirts.
I'm in
Chandigarh is very
Pune.
famous for
I'm
wearing.
in Pune at the moment, so here the weather is very nice.
Very nice, yeah. Right, good. So I will lecture till 2:50, I suppose. Yes, is that correct?
It's up to 3.
Is 1 hour, sir. Total is 2 to 3 p.m.
Including
Yes,
question
yeah,
answer.
Yeah, including. So I should
No.
stop a bit early.
There's no
Bit
question.
earlier.
There's no questions entertained in the
There are no
real talks.
I suppose.
Okay.
You can take 55 minutes roughly. I mean, it's up to you.
Oh, okay. Yeah, so I should not overshoot 3 p.m. Yeah,
Yeah, that is true because the next one is started more or less immediately.
immediately. So better to go till 2:55. Yeah, that's what I'm trying to do.
Yes, sir. Shall I start, sir?
Yeah, start now.
Yes. Good afternoon to one and all. On behalf of the organizing committee, IMS 2020, I welcome all of you for this Raj Gupta Memorial Award lecture by Professor Dinesh Khurana, chaired by Professor S. Armugam, sir. On behalf of organizing committee, I welcome Professor S. Armugam. He is a well-known graph theorist. He is the editor-in-chief of AK International Journal, and he is a past president of IMS. Sir, I welcome you for chairing this session. On behalf of organizing committee, I also welcome Professor Dinesh Khurana. And now I hand over the session to Professor Armugam, sir. Over to Armugam, sir.
Thank you. So I welcome all the participants, delegates for this 31st Hansraj Gupta Memorial Award Lecture in the 86th Annual Conference of the Indian Mathematical Society. The lecture is to be delivered by Professor Dinesh Khurana from Department of Mathematics, Punjab University, Chandigarh. And he's going to give us some ideas about non-commutative ring theory, which is going to be quite interesting to most of the participants of this conference. because nowadays there's a very close interaction between ring theory and graph theory. From ring theory, we develop zero divisor graph, and people talk about labeling edges of a graph through ideals of a ring and getting some new results. But all those theories are only for commutative rings. I'm just wondering how non-commutative ring can be used to bring into graph theory, in which case the graph should become directed graph. So perhaps your lecture will lead us to new ways of looking at directed graphs through non-commutative ring theory. So let's look forward to an exciting lecture by Professor Khurana. I welcome him to deliver the talk now.
Yes, okay, thank you, Professor Arumugam. Yeah, so I fear that my lecture will not have any connections with graph theory, but yeah, I know that there are a lot of people studying graph theory, our commutative rings, and perhaps some people from Iran study graph theory, our non-commutative rings also. So if I get to know some good references, I will definitely let you know. So at the outset, I would like to thank Indian Mathematical Society for choosing me for this honor. This honor becomes all the more profound by the fact that it's named after one of the founding fathers of our department, Professor Hansraj Gupta. So Professor Hansraj Gupta, we have heard a lot about him from our ancestors, from my supervisor, and in our mind, he has saint-like image. So heard so many wonderful things about him. Have never met him. I came to Punjab University to do PhD in 1996. So he had left for his family abode in 1988. So I have never met Professor Hansraj Gupta, but have heard a lot about him. So a few interesting facts about Professor Hansraj Gupta are that MathSciNet lists about 150 research papers of Professor Gupta, mostly in number theory and combinatorics. And according to his collected works published by RMS in 2013, these collected works were published in two big volumes. So Professor Hansraj Gupta, according to these collected works, has published 190 research papers and 6 books and monographs. Right. His address number is 1. And so interesting fact is that his beautifully handwritten PhD dissertation of 1936 is available in the library of our department. Written in such a wonderful handwriting, so it almost looks like a print. And another interesting fact about this PhD thesis is, if I am correct, that it was written without any supervisor. So Professor Hansraj Gupta did his PhD without any supervisor, right? So he was, as I told you, one of the founding fathers of our department, and our department building is named after him as Hansraj Gupta Hall. So all these facts make much more happy that this award is bestowed upon me. So now I come to my lecture. So at the outset, few disclaimers. So our rings will be with identity. So in all this lecture, all rings are with identity, because rings without identity is a altogether different world. It's a crazy kind of world. In rings without identity, you may not have any maximal ideals. Maximal ideals may not be prime ideals in rings without identity. For example, if you take ZP group, cyclic group of order P defines zero multiplication. Zero is a maximal ideal, but it's not a prime ideal. So things are very crazy in rings without identity. And the very fact that in which we learn in commutative algebra of rings with identity, that an ideal is maximal if and only if modulo this ideal, the thing becomes a field. This also no longer is there. So if you go model a maximal ideal in a ring without identity, you may not even get a domain, leave aside a field. So that's a very crazy world, so we'll not go there. So all rings are with identity unless otherwise stated. If there are some rings without identity, I will explicitly mention that. Right, so discovery of this non-commutative ring, business started essentially with Hamilton discovering quaternions in 1843. So after that, many leading mathematicians took fancy to non-commutative ring theory. Mathematicians like Wedderburn, Artin, Richard Brown, Nathan Jacobson, P.M. Cohen, Noether, Amritsar, Hurstein, and more recently, mathematicians like Goodall, Donald Passman, George Bergman, T.Y. Lamb, Agatha, to name a few. Right? So many leading mathematicians have studied non-commutative ring theory since Hamilton's wonderful discovery of Hamilton quaternions in 1843. So let's discuss a few themes which are prevalent in non-commutative ring theory. So since the discovery, right? So here are a few themes. So since Wedderburn proved the wonderful result that a finite division ring is a field in 1905. Yeah, this was very, this is a wonderful result because very unexpected because why should order imply something like commutativity? So it says that if the order of a division ring is finite, commutativity comes somehow, right? So this is a wonderful result proved by Wedderburn in 1905. So it started a major area of research in non-commutative ring theory called commutativity results, which involves imposing conditions on rings which imply commutativity, right? So, and this theme has been very fashionable for a very long time, and hundreds of research papers were written in this theme by Hurstein, Jacobson, Kaplansky, that impose some condition which visibly looks weaker than commutativity, and then that condition implies commutativity. For instance, if some power of an element of a ring becomes itself for every element, then the ring is commutative, right? And several such results, but this theme is no longer fashionable because a saturation point has reached. So you do whatever you do, somebody might have already done it some time ago. So this theme is no longer fashionable. Although if you put commutativity in Google, in MathSciNet, you will find hundreds and hundreds of research papers written on this theme. So this has been one of the prevalent themes of non-commutative ring theory. Right. So another is to see whether a property is left-right symmetric. So non-commutative ring theorists are always worried about this. You define some property of a ring, so you ask whether it is left-right symmetric or not. For example, chain conditions, Noetherianness, Artinianness. Define whatever condition you have. So you ask whether this condition is left-right symmetric. So for instance, few conditions which are left-right symmetric are, right. So some property which are left-right symmetric are semi-simplicity, semi-perfectness, strongly pi-regularness, exchange property. These are left-right symmetric properties. And some properties which are not left-right symmetric are Noetherianness. So a right Noetherian ring may not be left Noetherian. Right Artinian ring may not be left Artinian. Right perfect ring may not be left perfect. And similarly, right primitive ring may not be left primitive. These are just a few random examples of properties which are not left-right symmetric, and there are some properties I have listed which are left-right symmetric, right? So another major theme of non-commutative ring theory is to study the properties which vector spaces have. Right? So we know that almost none of the properties which vector spaces have go to the modules. So then you start studying those modules which have that vector space property. Like, so you study modules, for instance, for which every subspace is a direct summate. Or you study modules which have a basis. Right. You should study modules in which any two bases have the same number of elements. We know all of these are basic properties of linear algebra, right? Or you study modules such that every epimorphism going on to these modules split, right? So all these properties are there true for vector spaces. Then you try to see which modules do have these properties, and you get a different class of modules, you study those modules. So this is another theme which is prevalent in non-commutative algebra, or for that matter, algebra at large. Right. So another major theme is in non-commutative ring theory is that you see what results of commutative algebra are true in non-commutative algebra. Right. So almost none of these results which are true in commutative algebra are true for non-commutative rings, right? So you try to see whether you can impose some property weaker than commutativity to restore this result, or so this is another major theme of non-commutative ring theory. You see which results of commutative algebra, which well-known results of commutative algebra can be pushed to non-commutative ring theory, right? So in this talk, most of this talk will be based on this theme only. So we'll discuss few results of non-commutative ring theory, which can be pushed to commutative ring theory, which can be pushed to non-commutative rings, and some results which can't. And then you get in the bargain some very hard problems which so far no one has been able to answer in non-commutative ring theory. So we'll give some examples of those hopeless problems of commutative ring theory which can't be pushed to non-commutative ring theory, and some problems for which you can find an analog so that the corresponding result in commutative algebra becomes a special case. Right. So this will be the major theme of this lecture today. I will not be discussing other themes. So other theme is that central simple algebras also are a major theme of study in non-commutative ring theory, group rings, but will not go into that direction. So another disclaimer is that most of this talk will be non-technical and in some sense elementary also, but I hope not boring. Right. So that's my hope. So let's start with some basic properties of commutative rings. Right. So all of us know that sum of two nilpotent elements in a commutative ring is nilpotent. So in particular, some set of all nilpotent elements form an ideal in a commutative ring. And this ideal coincides with the intersection of all prime ideals. And it's called, so nil radical, that is the set of all nilpotent elements coincides with the prime radical, is the intersection of all prime ideals, right? So it's also then trivial that sum of two nil ideals is also nil in a commutative ring, because sum of two nilpotent elements is nilpotent. So sum of two nilpotent nil ideals. An ideal is called nil if its all elements are nilpotent. So sum of two nil ideals is also a nil ideal, right? But here you see that if I take this ring, 2 cross 2 matrix ring over any ring R, then take these two elements 0, 1, 0, 0 and 0, 0, 1, 0. Both of them are nilpotent with square 0. But if I sum these two elements, you get a unit. That's not a nilpotent. So sum of two nilpotent elements may be a unit in non-commutative rings, right? Also, the intersection of all prime ideals, which in a commutative ring coincided with the set of all nilpotent elements of a ring. In non-commutative rings, the intersection of all prime ideals may not contain any nilpotent element other than 0. Right. So things are quite far from commutative ring theory. For instance, if I take 2 cross 2 matrix ring, our ring of integers, or 2 cross 2 matrix ring, our any field F, right? Then if you take intersection of all prime ideals, it is 0. But there are so many nilpotent elements sitting inside these rings, which are non-zero nilpotent elements. So in non-commutative ring theory, the intersection of all prime ideals, although it is nil ideal, but may not contain any non-zero nilpotent element, unlike commutative rings, right? Okay, so in fact, the definition of even the definition of prime ideals which we take in commutative ring theory doesn't work in non-commutative rings. So if, for example, if I take this ring of 2 cross 2 matrices, our any ring S, take S to be any ring and take 2 cross 2 matrix ring over S, and take this element A is equal to 0, 1, 0, 0. And square of this belongs to every ideal. But this element doesn't belong to any ideal of the ring, because ideals of M2S are of the form M2I, where I is an ideal of the ring S. So this element A does not belong to any ideal, right? So what does this imply? This implies two very interesting facts. First is that the complement of no ideal in this ring R is multiplicative. So in particular, the complement of prime ideals is also not multiplicative, unlike in commutative ring theory. Commutative rings, you take prime ideals, their complements are multiplicative, then you have very important concept of localization. One of the most important tools in commutative algebra is localization. And localization works because the complements of prime ideals are multiplicative. But here you see that complements of prime ideals are not multiplicative. So this very important tool of localization, which is available to us in commutative algebra, no longer available in non-commutative rings. Also, if I take the definition of prime ideal, element-wise definition of prime ideal of commutative rings, then this ring has no prime ideal, because the square of this A element is in every ideal, but this element doesn't belong to any ideal. But that doesn't mean that this ring doesn't have any prime ideal, because every ring with identity has maximal ideals, and maximal ideals are prime ideals. So this ring indeed has prime ideals, but we have to take relaxed definition of prime ideal. We cannot take the definition, element-wise definition of prime ideals, which is there in commutative ring theory. So in non-commutative rings, we replace elements by ideals in the definition of a prime ideal. An ideal P is said to be a prime ideal if whenever product of two ideals is sitting inside this, then one of these two ideals is sitting inside this. Element-wise definition is too restrictive for non-commutative rings. So prime ideals definition is also different. Okay. So now I come to a very old open problem of non-commutative ring theory. In fact, one of the oldest. And the problem goes like this. So if I take an ideal I in a ring R, not necessarily commutative, I is a two-sided nil ideal and J is a nil right ideal, then I plus J is also nil. And a very easy proof is that you go modulo this ideal I. We know that taking factor by two-sided ideals is allowed. Taking factor by one-sided ideal is not meaningful, right? So you just go modulo I. If you take any element A plus B in I plus J, you go modulo I, you are left with B plus I in R mod I. And since B is nil, some power of B goes inside I is also nilpotent. So B becomes nilpotent. So this X sum of two. So every
Your audio is missing.
Hello, sir.
Audio is not.
I think there is some network issue, sir.
Okay.
Hello, sir. Dinesh Khurana, sir. Sir, Khurana, sir, please unmute yourself.
Yes. So am I audible?
Yeah, I think
Well,
there is some disturbance is coming, sir. I mean, some break is coming in your audio.
Yes, can
Yeah, hello. Yes. Yes, sir.
the sum of 2-0 right.
Sir, your voice is breaking, sir. Khurana, sir.
Prasad sir, from his end, network problem is there.
Yes, sir. Yes, sir.
He has to rectify, otherwise it will be.
సార్ దినేష్ ఖురానా ఫోన్ నెంబర్ ఉందా సార్? ఆయన బ్రేక్ అవుతుంది, ఆయన నెట్వర్క్ ఇష్యూ ఏదో ప్రాబ్లం ఉంది. అండ్ 1 minute.
So is everything fine now? So these are equivalent conditions. Sum of 2 nil left ideals is nil. Sum of 2 nil one-sided ideals is nil. Even if you take one right ideal and one left ideals, the sum is nil. Every one-sided ideal is contained inside. Then so this is also 2s. So you don't send matrix ring, just matrix ring of nil ring. That means nil ring means every element of S is nilpotent. Then so is M2S. This is also equivalent to Cauchy's conjecture. for any ideal, any nil two-sided ideal of a ring R, Ix, the polynomials with coefficients coming from this ideal I is contained inside the Jacobson radical of Rx. All of these are equivalent to Cauchy's conjecture, these so far, right? So another interesting properties of commutative polynomials of polynomial is invertible if and only if this constant term is invertible and all the other coefficients are nilpotent, right? But if you take this ring 2 cross 2 matrix ring over Z, then take this polynomial 0 1 0 0 plus 0 1 0 0 x. So the constant term is unit and the coefficient of x is nilpotent, but the polynomial is not invertible, right? And if on the other hand I take this polynomial 1 0 polynomial be so in fact to be in non-commutative rings. So another such problem is of seeing whether a square matrix is invertible or not. Our commutative rings, you just take a determinant of this matrix, and if the determinant is invertible in the base ring, we conclude that the matrix is invertible. And in fact, we then can find out the inverse also. But in non-commutative rings, since the determinants are not available and determinants, so to see whether a matrix, square matrix is invertible or not is a very hard problem. So even if we know that even if we are given that some matrix, n cross n matrix is invertible, so it's almost impossible to find the inverse of that matrix. So there's another very hard problem of in non-commutative ring theory, which is almost trivial in commutative algebra. Right. So here's another interesting fact of commutative algebra. So in McCoy in 1942 proved that if a polynomial is a zero divisor in the polynomial ring, you take any commutative ring R, you take its polynomial ring Rx, and if fx is a zero divisor in Rx, then fx is already killed by some constant, non-zero constant, right? So this was interesting fact proved in 1942 by Neil McCoy, right? If fx gx is equal to 0, if fx is killed by some polynomial, then it's already killed by some non-zero element of the ring. So it's killed by a polynomial of degree 0, right? So let's see whether this can be pushed to non-commutative rings. So in particular, if any polynomial is zero divisor in Rx, then all its coefficients are zero divisors. And all of them are killed by some one non-zero element in the ring, right? So in particular, so if you take a polynomial with whose one of the coefficients is invertible, such a polynomial cannot be zero divisor in polynomial rings, right? Because all of the coefficients have to be zero divisors in commutative rings. But now let's see what's the situation in non-commutative algebra. So here, so let me take any ring S and take 2 cross 2 matrix ring over S. Take this polynomial fx is equal to, which is there on the screen, fx is equal to 0 1 0 0 1 0 0 1 x plus something x here, right? You can see that in this polynomial, the coefficient of x is identity. unit. So one should expect that this polynomial is not a zero divisor if the things of commutative algebra are to be believed here. But interestingly, this is a zero divisor polynomial. If I take gx to be this polynomial, 1 0 0 minus 1 0 0 0 plus this written on here on the screen, then one can easily check that fx into gx is equal to 0. So in non-commutative rings, a polynomial whose some of the coefficients are invertible, such polynomials can also be zero divisors, right? Unlike in commutative rings, right? So then what are the polynomials in our non-commutative rings which have this property, McCoy property, that whenever they are killed by some polynomial, whenever they are zero divisors, they are already killed by some non-zero element of the ring. So we could generalize this McCoy's result as following, that fx, any polynomial fx, is killed by some non-zero element of the ring on the right, if and only if there exists a polynomial gx such that fx times c into gx is equal to 0 for every c in the multiplicative monoid generated by the coefficients of fx. So c is coming from the multiplicative monoid, that is multiplicative semi-group with identity generated by the coefficients of fx, right? So if I am over a commutative ring R, then this property is trivially satisfied. Whenever fx gx is equal to 0, you put in anything between fx and gx, that thing is also 0 due to commutativity, right? So this generalizes McCoy's result. And one may wonder that if in this result I can replace these C which are coming from multiplicative monoids generated by the coefficients of fx to the coefficients of fx. Can I strengthen this result where C is coming from the coefficients of fx? No, the answer is no, as the following example shows, right? So the above result does not hold if we restrict C to the coefficients of fx. So here's an example, right? So take R to be M5S, S any commutative ring, S any ring, not even commutative, any ring with one, right? Take this polynomial, fx is equal to A plus bx, where A is this 5 cross 5 matrix and B is this 5 cross 5 matrix. Then one can check that fx gx is equal to 0, fx times A gx is equal to 0, and fx times B gx is equal to 0. But still, this polynomial is not killed on the right by any element R of the ring, right? So that means in this theorem, we cannot replace these elements, these C coming from monoids generated by the coefficient of fx by the coefficients of fx. It's not possible. So this, in some sense, is the best possible result in that direction. Right. So more on the polynomials over non-commutative rings. We know that this evaluation map, fx going to f of a from Rx to R, is not a homomorphism if A is not a central element of R. So what does that imply? In particular, a root of polynomial fx may not be a root of fx into gx, right? Unlike in commutative algebra. So if something is a root there of fx, then it's also a root of fx gx. But since this evaluation map is not a homomorphism, so it no longer is true here, right? Also, on the other hand, a root of fx into gx, even over a domain, may not be a root of gx. So as a consequence, we may have that a polynomial of degree n has more than n roots. That's also possible. For example, in Hamilton quaternions, if I take x square minus 1, it has infinitely many roots, right? So So things like, so here in Hx, k is root of x square plus 1. And x square plus 1 is x minus iota into x plus iota. But k is neither a root of this nor a root of this, right? And as another example, here, iota is not a root of product of x minus I, x minus j. If I take this product, I get this polynomial, our Hx. H is Hamilton quaternions. But you can see that iota is not, I is not a root of this, right? Although in this product, it is root of this thing, right? But on the other hand, j is root of this, j is a root of this also, one can check, right? But this is not any coincidence which is happening here. It's always true, and this fact has a interesting consequences. So the fact in non-commutative ring is also that if it is true that a root of gx is also a root of fx gx. We saw above that a root of fx may not be a root of fx into gx. But on the other hand, one can prove that a root of gx is always a root of fx into gx. In polynomials, our non-commutative rings also. And this fact has very interesting consequences. Let me list few of the consequences of this, right? So if we take any square matrix, our commutative ring, then the Cayley-Hamilton theorem says that that A satisfies determinant of A minus xi, right? If I take determinant of A minus xi, so multiply that polynomial is in Rx. If I multiply that polynomial with identity, we get a polynomial in Mn Rx. Cayley-Hamilton theorem simply says that A satisfies this new polynomial, determinant of A minus xii. That's Cayley-Hamilton theorem, all of us know, right? So you see, here's a proof of Cayley-Hamilton theorem based on that interesting property of polynomials, our non-commutative rings. So if I multiply A minus xi by adjoint of A minus xi on the left, I get determinant of A minus xii. So all of these three things are polynomials, our non-commutative ring MNR. So this is also adjoint of A minus xi is a polynomial, A minus xi is a polynomial, determinant of A minus xi into I is a polynomial. So this is the same situation, fx gx is equal to hx type polynomial, right? So if you believe that result, that whenever that a root of gx is also a root of fx gx, now since A satisfies A minus xi, so A must also satisfy determinant of A minus xi into I. That is Cayley-Hamilton theorem, right? Right. So, right. Moreover, in fact, you can get a better result than Cayley-Hamilton theorem. So, better result is that if A, this matrix, n cross n matrix of our commutative ring R, satisfies any polynomial in MNRX, not just A minus xi. So A minus xi is a simple polynomial which A satisfies. Now I am here saying that whenever A satisfies any polynomial fx in MNRX, then A also satisfies determinant of fx into I. Right? So this is interesting generalization of Cayley-Hamilton theorem coming from that very simple fact about polynomials, about the roots of polynomials in non-commutative rings. And this fact was well known to mathematicians a century ago. So in fact, old textbooks, if you look at old 100-year-old textbooks of linear algebra, so there Cayley-Hamilton theorem is proved as a corollary of this more general fact that whenever A satisfies some polynomial, so it satisfies also the determinant of that polynomial. So this generalization was known, but somehow on the way it got lost. No textbook of linear algebra mentions it anymore, right? So, and the moral of the story is that the proof that A satisfies A minus xi implies that A satisfies determinant of A minus xi is not an incorrect proof of the Cayley-Hamilton theorem, as one might like to believe, right? Students generally in the class come out with this proof. Since A satisfies A minus xi, it satisfies a determinant of A minus xi, then we go to long lengths in explaining to them that this is not an genuine proof. But after this theorem, this is a genuine proof that A satisfies A minus xi already implies that A satisfies determinant of A minus xi, because whenever A satisfies any polynomial, it satisfies its determinant also. Right. So that's interesting. And moreover, much more generalized fact than this is true. Much more generalized fact that Cayley-Hamilton theorem is true, and that follows from this recent result of ours. So in fact, if you have any three polynomials, f, g, h, this polynomial ring, in n variable, any ring R, right? So if h is equal to f into g, then h a1 a2 an is contained in the ideal generated by g a1 a2 an for every pairwise commuting elements a1 a2 an of ring R. In particular, if g a1 a2 an is 0, then h a1 a2 an is also 0, right? So this has a corollary to this, in the same way as we proved Cayley-Hamilton theorem just a moment back. One can prove this result. If S is let S be a commutative ring, and you take any polynomial f in n variables over this ring M and X, if A1, A2, An are pairwise commuting matrices, such that f A1, A2, An equal to 0, and G is determinant of f into I. So G must also be a polynomial in n variables over this ring M and X. That these A1, A2, An satisfy this G also. That is G A1, A2, An equals to 0 also. Cayley-Hamilton theorem is just n equal to 1 case of this result. And this result was proved by Phillips in 1919. It's very old result, but then there the proof is different. Not this one which I'm giving here. I'm driving it as a simple corollary to a very well-known fact about polynomials, our non-commutative rings. Okay, so then some natural questions which come to mind, that are these result like Cayley-Hamilton theorem through our matrix, our non-commutative rings also, right? So what do we have in view of Cayley-Hamilton theorem? Cayley-Hamilton theorem says that any n cross n matrix over any ring R satisfies a polynomial of degree n over R. It's integral over R, and it satisfies a polynomial of degree n, right? And that polynomial is determinant of A minus xi. So since determinants are not available for matrices over non-commutative rings, but at least we can ask this question. Suppose we have an n cross n matrix over a non-commutative ring R. Does it satisfy some polynomial of degree n over the ring, base ring, right? So that question can still be asked. And so easy, no answer comes from this result, that if every T and R is upper triangular matrix, n cross n upper triangular matrix. If every n cross n upper triangular matrix satisfies a monic polynomial of degree n over R, then the ring R is already commutative. So you cannot hope to have anything like Cayley-Hamilton theorem over non-commutative rings. That's not possible. Even upper triangular matrices do not satisfy monic polynomials of degree n over the base ring if R is a non-commutative ring. Okay, so upper triangular matrices are no good. So at least we can ask whether diagonal matrices n cross n, suppose I take an n cross n diagonal matrix over this ring R. So does this satisfy a monic polynomial of degree n with coefficients from R, right? At least is Cayley-Hamilton theorem true at this level, at at the level of diagonal matrices our non-commutative rings? So answer still is no. But then you have a nice result like this. So the following result exactly characterizes those rings over which every n cross n diagonal matrix satisfies a monic polynomial of degree n over r. These rings over which this happens turn out to be left duo rings. A ring is said to be left duo if every left ideal is a two-sided ideal. And if this is so for 2 cross 2 matrix rings, it's already true for every n cross n matrices. So if every n cross n diagonal matrix satisfies the monic polynomial of degree n over r, if and only if every 2 cross 2 diagonal matrix satisfies the monic polynomial of degree 2 over r, if and only if the ring is left duo. So this gives a characterization of very interesting classes of rings called left duo rings, in which every left ideal is two-sided ideal. Right. So one may wonder, can I relax this condition of degree? So we are now, so far we have been asking whether an n cross n matrix of different types satisfies the monic polynomial of degree n. So let's relax this condition, since we are not able to do this. So now at least can we ask this question, that every n cross n matrix of any form, even diagonal matrix, satisfy a polynomial of any degree over r, right? So don't put this condition of degree also. Still that is not true. If this happens, if every diagonal matrix, n cross n diagonal matrix satisfies a monic polynomial over r of any degree, then the ring should be a Dedekind finite ring. So already there is condition on the ring. A ring is said to be Dedekind finite if every left invertible element is right invertible and vice versa. Such rings are Dedekind finite rings. That is, one-sided invertible elements are invertible. Such rings are said to be Dedekind finite rings, right? So let me skip a few slides. And as I've already told, that to check whether a matrix is invertible or not is very difficult. So let me come to the last problem, because time will permit only that. So we know that our commutative rings, transpose of every invertible matrix is invertible. This can be seen via determinants, and this can be seen via the property that AB transpose is B transpose A transpose. So one may ask, if this is true our non-commutative rings also, if I take a square matrix and suppose this square matrix is invertible, and then I take its transpose, then is the transpose also invertible? So the answer is no, it is not. A classical fact is that if our division ring transpose of every, if you take matrix M and D, where D is a division ring, and if the transpose of every matrix over this ring is also invertible, then D must be a field. One may wonder if there are generally non-commutative rings which are not commutative, over which transpose of every invertible matrix is invertible. So we could characterize these rings some time back, and the characterization is given here. So in this theorem, AB will denote commutator, AB minus BA, and AXB will denote generalized commutator, AXB minus BXA. So the theorem goes like this: the transpose of every invertible matrix is invertible over R if and only if the ring modulo its Jacobson radical is commutative, if and only if 2 cross 2 special 2 cross transpose of these special 2 cross 2 invertible matrices is invertible. So you don't have to look at n cross n matrices. Even if 2 cross transpose of 2 cross 2 invertible matrix is also invertible, still you get this characterization. You just have to look at 2 cross 2 matrices also. So here, if A plus BC is unit, implies A plus CB is unit. This is also equivalent condition. Unit plus commutator is in unit for every unit in U. 1 plus AXB is a unit. X plus ABC is a unit. So for rings with Jacobson radical, all of these conditions listed in this theorem give you commutativity results, that they apparently look weaker to commutativity, but they imply commutativity of R if Jacobson radical is 0. So you get few commutativity results as an accident from this theorem already, although it was not intentional. So our aim was to characterize rings our which transposes of invertible matrices are invertible. So I think I am running short of time, so I better stop here. Thank you.
Let us thank Professor Hansraj Gupta for memorial lecture of Professor Khurana for his excellent expository survey of results on non-commutative rings. Thank you very much.
Thank you, sir. Thank you.
Yes, Arumugam, if you permit, I would like to make certain remark not about the lecture, but about Professor Hansraj Gupta.
Fine.
I had the pleasure and privilege of spending some time with him at Allahabad when I was at Mehta Research Institute. Professor Hansraj Gupta had settled in Allahabad, and he was a frequent visitor to Mehta Research Institute. He was a very nice human being, very fragile, but very active. For any lecture, any seminar, he would be coming to Mehta Research Institute. If Rishi Kumarji, is it possible to share one of the screenshots which I can put it here?
Yes, sir. Yes, sir. In fact,
he had prepared a perpetual calendar.
Yes, so I will stop sharing.
Yeah.
Right, you can go ahead now. Yeah.
So he gave a copy of that the calendar to me, which I had put it on my Facebook long back. And I just got the copy of that, and let me see if I can share that with you. Because this is so nice to recall that part. So I'm just trying to share it here.
Can I share, sir?
Let me see if I can do that.
Yes, sir. You can share it, sir. Krishandra, sir. You have the co-host.
Sir
so you
also
can
can
share.
share, sir. Yes.
How do I do that? Desktop?
Share screen.
Yeah, I
Click
set
on-
share screen. Then share
And
comes
then-
here.
Yes, sir.
Then
Below share, click on again share button, sir.
share. No. I put it share
Click-
screen.
Yes, sir. Then in the first, you can select the first screen, sir. Select. Then below one more button will be there. Share button will be there. You click
Share
on that
button
share
is
button.
there.
In blue share button will be there, sir. Blue color.
Then it says cancel or open system preferences. Shall I say that? No.
Sir, no, sir. In the
No, if
right
you click on,
corner, there is
if
a
you click on share screen, sir, you will get a window.
No, I say share screen. So I get a share screen.
Yes,
Yeah,
sir.
then you click on desktop.
Desktop.
Click on
Okay.
Click on desktop and then move
Share.
towards right. Then yeah. So desktop, you should. Do you have this file on your desktop, sir?
Yes, I have.
Yeah, now
So
it is sharing.
we just share.
yes, we are there. Right.
It is allows Zoom to share your screen.
Yeah, we
Yes,
are
sir.
able to see this. You are already sharing it, sir.
No, this is actually Rishi Kumar, sir.
Okay,
I
this
was
is Srivastava. Okay, this is.
It's okay, sir. It's
I think you could send it to him, maybe email it to him. Email.
Yeah, I'll do
Co-host
that.
can share it.
Yeah, I'll send it to him.
yes, sir. This is the summary link sent by Professor Piyush Chandra, sir, regarding Professor.
No, I was sending something else.
Yes, sir.
We still have a couple of minutes, so I'll send it to just now.
Yes, sir.
I send it by email, right?
Yes, sir. Yes, sir. Right, sir.
So if I might say so, Professor Dinesh Khurana, excellent lecture. This is Suri here.
Oh, so
Very
thank
interesting.
you. Yeah, right. So I mentioned that this commutativity business is no longer in fashionable. We learned it hard way, Professor Suri. You remember?
Very nice lecture.
Right.
Do I share it now? I'm just sending it.
Sir, Suri sir, your mic is muted, sir.
Oh, sorry. So if I might just say one comment with the permission of the chair. Professor Dinesh Khurana mentioned about invariant basis number.
Yes.
So that is to do with graph theory quite a bit nowadays. There is this Levitt path algebras.
Yes, good path algebras. Yes.
So Levitt was the first person to produce a class of examples where the different basis cardinalities are possible, free modules. And he produced graph theory. Now there is a big industry working on Levitt path algebras.
Big industry. So almost everyone is moving towards that. Right.
Very nice.
Yes,
Rich theory.
Correct. That's correct. Yeah.
Thank you.
Hello.
Yeah, I've just sent it to you. I don't know whether it's possible.
To me or Dinesh Khurana, sir?
No. I have sent it to Professor Rishi Kumar.
Yes, sir. I am checking.
Maybe I sent it to Dr.
Rishi Kumar.
Yes, sir.
Rishi Kumar. This calendar he had prepared when he was in Patiala. So before joining Chandigarh, he was there. And he says it's a perpetual calendar, giving a partition and things like this. And he has given the example also how to read it. Did you get it?
Yes, sir. Just now I see it. I'll just open, sir.
Dr. Rishi?
Yes, sir. I'm just
here. Yeah, good afternoon. So we have 5 more minutes, no?
Yeah,
yes,
just
sir,
a moment. Sir, yeah, this is the calendar which he has given. Perpetual calendar prepared by Professor Hansraj Gupta of Samna, Patiala. Long back. If you put the second photo also.
Yes, sir. Yes, sir.
Yeah. So he gave all these tables and then how to find out the dates, etc., from there.
Yeah, that's amazing. That's amazing.
That's amazing.
So how much hard work he has put into.
Maybe I'll send it to you if you're patient. Okay, then.
Maybe his collected works perhaps has these things.
Possibly, yes. I don't know.
Yes, possibly, yes. Yeah.
So this is another one you shared me, sir.
Yeah, but this is the example and how to find out how to get that together.
Yes, sir. Divide the year in question by 400 and find out the letter at the end of the column in which the remainder lies. Use table number 1. Yes, sir. It is based on the previous table. Yes, sir.
It was in the year 1923. See, down.
Yes, sir. 23 September.
I was just amazed the way he had gone. Thank you, Professor Dinesh Khurana. It was nice having you.
Thank you, sir. Thank you.
Professor Sudeep Ghurpade is there. It's all for him to take care. Apparently, Professor A.K. Agarwal is there.
Professor Agarwal is there?
Is here. Sir, mic is muted. Yes.
And Professor Dr. Tanti is there?
Yes, sir.
Regarding certificate.
Am I audible, sir?
Yes, you're audible.
Wait, sir. Sir, on behalf of the...
You want to try to share your slides, Dr. Tanti?
Yes, sir.
We just test it out.
Yes, sir.
Sir, just a minute, sir.
Yeah. I know we have 2-3 minutes.
Yes, sir. I would like to thank the chair, Professor Armugam, and also the wonderful talk given by Professor Dinesh Khurana.
Yes, of course.
Sir, on behalf of the organizing committee, we would like to ask and request the chair, Professor Armugam, sir, to hand over the certificate to Professor Dinesh Khurana. Please announce, sir. Dinesh Khurana, sir, please.
Vedas, sir.
Yes, sir. You please just say that the certificate is handed over to...
Yes, I'm happy to hand over the certificate to Professor Khurana. So here is the certificate.
Yes, sir.
Thank you. Thanks a lot, sir. Thanks a lot.
31st Hansraj Gupta Memorial Award Lecture on some glimpses into non-commutative ring theory, delivered by Dinesh Khurana. The certificate is handed over by Professor Armugam, sir, to Professor Dinesh Khurana. Thank you very much for...
Thank you. Thanks a lot. Receive.
Thank you. Thank you, sir, for we are on time. By 3:05, we want to have a next session. So we want to check the speakers as...
Sir, you have to make them Professor Jaganmohan Tanti as a co-host. Otherwise, he cannot.
Yeah, you should make him a co-host.
Yes, sir. Within a minute, sir.
Thank you, Dinesh.
Thank you, sir. Thank you. Thanks a lot.
Jagmohan, sir.
Yes, sir.
Yes, yes, sir. I'm just making you as a co-host.
Okay, sir.
Sir, now we can share the screen.
Yeah.
Okay, sir.
Just a minute. We want to introduce Sudhir Ghorpade, sir.
Can you make it full screen?
Yes, sir.
Sir, just a minute. We want to introduce the chair to the participants.
Okay, sir.
Sir, may I request Sudhir Ghorpade, sir, please.
Hello.
Yes, sir. Sir, may I welcome Professor Sudhir Ghorpade.
Sorry, my connection is not good. I will switch off my video.
Yes,
but
sir.
I'm
Fine,
there.
Fine, sir. Fine, sir. Professor Sudhir Ghorpade, mathematics professor at IIT Bombay, Mumbai. He is currently editor of the Journal of IMS. Was president of IMS in 2018-19. So thank you very much, sir, for helping us in all aspects. And we'd like to thank you for accepting the invitation and be the chair of this session. On behalf of IMS and on behalf of the organizing committee, IMS 2020, I warmly welcome Professor Sudhir Ghorpade, sir, for chairing this session. Now I'd like to hand over the session to Professor Sudhir Ghorpade.
Thank you. Thank you, sir. Actually, the person who needs to be thanked and honored today is Dr. Jagmohan Tanti. And as you know, he has received the Dr. A.K. Agarwal Award and he will be presenting his lecture. Are you ready, Dr. Tanti?
Yes, sir. Yes, sir.
And okay. And he will speak to us on Euler's criteria for Lth power non-residues with L prime. Dr. Tanti works at the Central University of Jharkhand at Ranchi. Over to you, Dr. Tanti.
Thank you very much, sir. First of all, I should be thankful to the Indian Mathematical Society to consider my work prestigious award, and I should be grateful to university also, where I could do this work. I should be also thankful to my supervisor, with whom I started this journey on Euler's criterion. So basically, Euler's criterion for Lth power non-residue with L prime, it has been started with smaller values of L, like L equals to 2, 3, 5, 7, 11, like that. And yeah, this work was started by Gauss, and it has been recorded there in his famous book, Disquisitions Arithmetica. So for L, this criterion is called as quadratic reciprocity law. Then for L equals to 3, also he has given some, but not whole. And later, Emma Lehmer had established the complete result. So let us, so I have tried to include the smaller, laws for smaller values of L also here to make it, yeah, so that we can see the history. So this is the outline of the topic. Yeah, so we will be talking about its short introduction and Euler's criterion regarded as reciprocity laws. So here basically we are using Jacobi sums and cyclotomic numbers to get the conditions. Yeah, so we will introduce Jacobi sums also, some historical background, quadratic criteria. Criteria for E means here L equals to means there I have written E because E is not necessarily prime. So because quartic conditions has also been obtained. So these are the smaller cases we are recording here. Non-results for general prime L. Then this Diophantine system is considered for the computation of Jacobi sums that we will show here. Then the criterion for prime order in the PID case, because this award has been given for this PID case, the paper on this PID case. Yeah, then we will talk about some conclusion and future scope. Yeah, so starting point which we can see from the Fermat's little theorem. If we have a positive integer coprime to an odd prime P, and E is an integer bigger than or equals to 2, then we know that d to the power P minus 1 is congruent to 1 modulo P. So that can be written as, because E is dividing P minus 1, the condition is there, P is congruent to 1 modulo E. Then this congruence can be written as this d to the power P minus 1 by E whole to the power E congruent to 1 modulo P. So we are looking here for the solution of this congruence, and this number represents the solution to this equation, y to the power E congruent to 1 modulo P. So, and the solutions of this congruence modulo P are the eth roots of unity modulo P. And yeah, so it has exactly E solutions. Yeah, and we fix our primitive root as gamma modulo P. Primitive root means the generator of FP star, the finite field of P order. It's FP star means just delete 0 element, then we see that is FP star is a multiplicative cyclic group, and its generator we have chosen here as gamma. Then gamma to the power P minus 1 by E is also a primitive eth root of unity modulo B. So yeah. So yeah. So in order to see this, let us first talk about what happens when we just replace E by 2. Then this condition, these two conditions of Euler's criterion is nothing but quadratic reciprocity law. So this is an extension of quadratic reciprocity law. But in quadratic reciprocity law, we see that only two roots of unities are there. These are +1 and -1. So the conditions for one imply that rest of the conditions will be true for the other one, for non-residues. But when we go ahead beyond 2, 3, 5, 7, etc., then there will be, if one integer d is not an eth power non-residue, then this d to the power p minus 1 by e may be some eth root of unity modulo p. So when this will be congruent to gamma to the power p minus 1 by e modulo p, for that condition, for that we want to find out the condition, compute the conditions here. So which is equivalent to say that index of d with respect to gamma is congruent to 1 modulo p. Yeah, so the congruence conditions we compute in terms of either cyclotomic numbers or Jacobi sums or solutions of systems of certain Diophantine equations. So at the beginning, Gauss and Williams and Lehmer, all of them have Diophantine equations, and they had obtained the conditions in terms of the solutions of those Diophantine equations. But the complexity of those Diophantine systems gradually increases as we gradually go from the smaller values of E to higher values of E. And for E equals to 13 onwards, we could not see any such Diophantine system with whose solutions we can talk about this Euler's criterion. But Jacobi sums are existing and cyclotomic numbers are existing, and these are easy to compute and see see the conditions with respect to the Jacobi sums. So that we have tried to exhibit here. Yeah, these are the certain criterion for smaller values of E. Yeah, so Euler's criterion states this, that if we have an integer d and pj odd prime, d and p are co-prime, then d to the power p minus 1 by e is congruent to 1 modulo p if and only if t is an eth power residue modulo p. But if d is not an eth power modulo p, then d to the power p minus 1 by e is congruent to alpha e, 1 eth root of unity modulo p. Yeah, so so this alpha e, when we fix that this is one particular eth root of unity, then what will be the condition? That is the this criterion. So yeah, this E equals to 2 is quadratic reciprocity law, E equals to 3 is cubic reciprocity law, and so on. So this is the definition of Jacobi sum. There are certain another type of definition also, but that differs by both of the definitions differ by just factor chi of -1. So yeah, so we are using this definition here. Yeah. So historical background, it has been started from Gauss, equals to 4 is also Gauss, equals to 8 Western and Lehmer, equals to 16 and 13 to Hudson and Williams, and so on. So our work, we started from E equals to 7. We can see that equals to 7, 11, myself and Professor Katre computed. Yeah, it is 4th point from the above. Then for E equals to L, there were certain criteria we had obtained for D equals to 2 and L in terms of coefficients of this Jacobi sum of order L. Yeah. So quadratic criteria is nothing but whatever we have studied as quadratic reciprocity laws. So I will not spend much time on this because we have already seen. Yeah. So d to the means when d is quadratic residue, then this d to the power p minus 1 by 2 is congruent to 1 modulo p, otherwise minus 1. This is the only choice. And Legendre symbol has been developed. So here our residue symbol will be developed. Yeah, this is cubic criteria. So we were talking about some Diophantine equations. So this is 4p equals to L square plus 27 m square. This is one of that type of Diophantine system, which was considered for L equals to 3. Yeah, so, and we can see that this 1 n plus 9m by L minus 9m, L minus 9m by L plus 9m, these are the 3 distinct cube roots of unity, out of which L plus 9m by L minus 9m and other one, except one, these are the primitive cube roots of unity. And so cubic criterion has been developed like this. If D is a cubic residue modulo P, then this D to the power P minus 1 by 3 will be congruent to 1 modulo P. Otherwise, this L plus minus 9m by L minus plus 9m. So ambiguity of sign was removed by conditions D equals to 2 and 3 in terms of coefficients of J3, Jacobi sum of order 3. So here ambiguity of sign has been removed by this last condition, like L congruent to M modulo 4 for 2. And similarly, M congruent to minus 1 modulo 3 in B. Yeah, 3. Yeah. So reference to quadratic equation P equals to A square plus B square, A congruent to 1 modulo 4, and Jacobi sum, corresponding Jacobi sum is J411, this thing. Yeah. So here, yeah, quadratic criterion has been recorded. So if D is a quadratic residue, if and only D to the power P minus 1 by 4 is congruent to 1 modulo P, otherwise it will be either minus 1 or A by B or minus A by B, because these are the 4th roots of unity except 1. Yeah. Some explicit criteria again here established. Yeah, for 2 and 5. This is for 5. L 5 Dixon system quadratic Diophantine equation is nothing but Dixon system. So system of Diophantine equations. Yeah, and for this is a solution. So such type of alpha 5 type of primitive 5th root of unity had been calculated. And we can see that this J115, which is the Jacobi sum of order 5, this has been written like this in terms of solution of this Diophantine equation. And this power residue symbol is nothing but replacement of Legendre symbol here. What Legendre symbol we were seeing for L equals to 2 quadratic case. So here power residue symbol we have defined, and this has been defined as for prime elements pi in the ring of integers of cyclotomic field of order L, Q zeta L. So yeah, so pi is a prime element, co-prime to L. Lth power residue symbol is defined like this. For any A we take in Z zeta L, then this symbol equals to 0. Value of this symbol is 0 if A is divisible by pi. If it is not divisible, then this will represent a Lth root of unity, such that this thing a to the power norm of pi minus 1 by L is congruent to a by pi L modulo pi. Yeah. So Quintic criterion had been obtained in terms of this power residue symbol for L equals to pi, and some explicit Quintic criterion I have recorded here for D equals to 2, 3, and 5. And this has been obtained by Katre and Rajwade. So this is for L equals to 7. Here we had started. So Williams had given the answer for first part of the Euler's criterion, like when some integer is 7th power modulo p, septic residue modulo p. For that he had given condition, but if it is not 7th power modulo p, then the other conditions we had obtained, yeah, with some explicit criterion. And this is the 72p equals to this quadratic Diophantine system was the system under consideration. And we had given here the expression for Jacobi sum of order 7 in terms of the solution of this Diophantine equation. Yeah. Septic criterion. So this Leonard and Williams has given the septic criterion. And then we had obtained the septic residue modulo p. Yeah. So here in the theorem we had recorded our condition that if D is co-prime to 7, then D is a septic residue modulo p if and only if this psi 7 by D 7 equals to 1. Otherwise, this D to the power p minus 1 by 7 is congruent to alpha 7. So alpha 7 is obtained in a particular way. So this is a particular primitive 7th root of unity, which will be similar to gamma to the power p minus 1 by 7. So that's why, and for that this condition has been obtained. Psi 7 by D 7 is equals to zeta 7 to the power 3. Yeah, this is about the septic case, and some explicit criterion has been obtained. D equals to 3 we have obtained here. I have recorded here, and yeah, so these AIs are nothing but the coefficients of zeta 7 up to zeta 7 to the power 6. Yeah, these are complex 7th roots of unity of the expression. Yeah, Jacobi sum. So explicit criteria for D equals to 2 and 7 have also been studied and recorded in the letters, right? So these are the general case. So this 11th criteria also we had obtained, and yeah, we have recorded here. Yeah, we can see that here, yeah, this theorem has been little bit elaborated for D equals to 7 here in the explicit 11th criteria. So yeah, so we can go ahead. So some known results for equal to L. Yeah, so Jacobi sum can be written as here a1n zeta L up to a L minus 1n zeta L to the power L minus 1. Okay. Then Satinder Pal, Pranami, and Agarwal, they had given the condition for 2 to be an Lth power residue modulo p as this thing. Summation of AI is of 1, yeah, congruent to 0 modulo T. Yeah. But when 2 is not an nth power modulo P, then index of 2 will be congruent to 1 modulo L if and only if this condition that AL minus 2th coefficient of J11 should be congruent to 1 modulo 2. This has been obtained by us. And for L also we had obtained this condition. If L is not an nth power and L is nth power, both conditions we had obtained and recorded here. So for computing Jacobi as we discussed earlier that for L beyond 11, there are no Diophantine system. So for that, these are the arithmetical conditions with which Jacobi sums of higher orders are being computed. Yeah, but this is also a little bit complicated. But later in the paper which is under which has been recognized for the award for, so in that paper we had tried for L less than equals to 19, we had given one idea to compute the Jacobi sum from Stickelberger theorem with less effort, much more less effort. We do not need to consider this arithmetical condition to compute that. Yeah. So yeah, with reference to the earlier 5 conditions, we will be getting some solutions as the conjugates of this Jacobi sum JL1n. But the 6th condition fixes the Jacobi sum, means this fixes the solution. Means along with those 5 conditions, the 6th condition, if we add, then we will get exactly one solution. Yeah. So this is the PID case which we had obtained in that paper. So this condition, so this is the Euler's criterion which we had obtained. There is an nth power modulo P if and only if this phi by dl is equals to 1, and otherwise the index of D is congruent to 1 modulo L if and only if this phi by dl is zeta L to the power such type of summation. And we have checked for L less than equals to 19, this summation, this which is occurring as a power of zeta L, this is not 0 modulo L, right? This is different. So this quantity zeta L to the power, this summation is different from 1. This is a Lth root of unity different from 1. So however, we expect that this theorem holds good for non-PID case also. Yeah. So we conclude that we have Euler's criterion of prime order L in terms of Jacobi sums of order L for the PID cases, means L less than equals to 19. And we hope that the same condition will hold for non-PID cases. And we assure you that we will try to make some advancement in this direction. That is, we will obtain Euler's criterion for, means generalize these results for a larger section of primes. So we are trying that thing. Yeah, so these are the references we are following. So yeah, so yeah, thank you, sir. If there be any question, I will be
okay.
Okay.
Thank you also for finishing in time, and I think that leaves us some time for questions. So, if anyone has any questions, just unmute yourself and ask the questions directly. And I'm sure Dr. Tanti will be happy to answer.
Yeah, sir. I will try from my side.
Let me see if there is anything in the chat box.
Okay, sir.
No, sir. No questions.
So I see that Professor Agarwal is here. Professor Agarwal is the person responsible for this award. I don't know if he wants to say anything.
To Professor Ega Agarwal, sir.
Some questions, some things, whatever.
Agarwal, sir, mic muted.
Okay. Yeah.
Am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So I wish everybody good success in this conference. And the lecture was good. And nothing more to say at this time.
Okay, sir. Thank you. Thank you very much.
Please open your video also, sir.
Thank you.
Yes, sir.
Of course, one question I had, you already sort of remarked, what happens when that cyclotomic integers is not a PID, sort of
yes,
greater than 1.
Yeah.
Is there any case where you know the answer, maybe for small class number or something?
Yeah, I am guessing that for regular primes,
yeah,
the same formula will hold, but some computations are needed.
Okay.
I have to do certain computations.
Okay.
For that.
Okay. Well, that will be a good extension, I would imagine.
For regular primes, it will be holding, I think.
Okay.
Yes.
It basically means prime which don't divide the class number, right?
Yes, sir. Yes.
And in what way you will use the regularity? You use the Bernoulli criteria? Or?
No, sir. We do not need that. We just need that the class number should be relatively prime to L. Just.
We request Jagmohan sir to show your video.
Yeah, Dr. Tanti, if you
Oh, sorry, sir. Sorry, sir.
maybe
Sorry,
you
sir.
can make yourself visible.
Yes.
Yes, sir.
Yes.
It is very cold here, so
Yeah,
have to be. Yeah.
Quite all right. Looks like there is no question. So then, on behalf of Indian Math Society and my own behalf, I'd like to congratulate you for receiving this award and thank you very much for this talk. Thank you.
Thank you very much, sir. This is like a blessing from Indian Mathematical Society and also.
Yeah, we hope you continue to remain active and do good work.
Sure, sir. Sure, sir.
Thank you.
Thank you.
Sir, on behalf of organizing committee, we would like to request Sudhir Ghorpade sir to hand over the A.K. Agarwal Award certificate to Dr. Jagmohan Tanti.
All right. So everything is working. So I'm happy to hand over the certificate for Professor A.K. Agarwal Award for the year 2019 to Jagmohan Tanti, which is given at this 86th annual conference of the Indian Mathematical Society. Congratulations once again.
Thank you, sir. Thank you very much.
So we would like to thank the chair, Professor Sudhir Ghorpade sir, for his valuable time in his busy schedule. And also we'd like to thank Professor Dr. Jagmohan Tanti for giving a wonderful talk. Thank you one and all. Please join us. Please continue in the same link. We'll have a next session.
Small break, no? 5 minutes?
Yes, sir, 5 minutes break, but now 3:35 we have to start, sir, actually.
Okay. Oh.
4:05. After that, we have a break, sir.
Okay.
After this talk. So we'd like to invite Professor M.M. Shikare, sir, is available. and
Yeah, I am there.
R.B. Yadav.
I see.
Yes, sir. We'll just make you as a co-host.
Mute and super video.
Mhm.
R.B. Yadav.
Hello. Huh.
I'm checking the R.B. Yadav is available. R.B. Yadav.
Yes, I'm here.
Name you are showing.
Yeah, I'm here.
Yeah, we could see.
Sir, we'll make him as a co-host. Sir, your voice is not audible, sir.
My voice is not.
Yes, Sikare, sir. Yes, sir.
Yeah, it is okay now.
Okay, sir. We just want to introduce you, sir. May I request Dinesh? Dinesh, sir, is available? Professor Dinesh?
Yes, I am available, sir.
Sir, I'm just asking our own faculty, Professor Dinesh.
Oh, I see.
Yes. Yes. So, on behalf of organizing committee, we welcome all of you for the next session, a Narsingh Rao Prize lecture by Dr. R.B. Yadav, Sikkim University, Sikkim, on some categories of Riemannian manifolds. We welcome you, Dr. R.B. Yadav, on behalf of organizing committee. It is a great pleasure and honor to welcome the chairperson, Professor M.M. Shikare. He is formerly professor of Shivaji Bhai Phule University, Pune, and presently he is the editor of Indian Mathematical Society Journal, Mathematics Student. Thank you, sir, for chairing the session Narsingh Rao Prize lecture by Dr. R.B. Yadav. Now the session is handed over to Professor M.M. Shikare. Over to Professor M.M. Shikare, sir. Voice is muted, sir. Please. Sir, your mic.
Sir, unmute yourself.
Yeah, I think now it is okay.
Yes, sir.
Yeah. So it's my pleasure to welcome all the participants for this lecture. As mentioned earlier, the lecture is given by Dr. R.B. Yadav, who was associated earlier to Statistical Indian Institute, Tezpur. Now he has been affiliated to Sikkim University, Department of Mathematics, Sikkim. You may be aware of the fact that the Indian Mathematical Society has instituted a Narsingh Rao Memorial Prize, which is given to the author of the best publication that is published in the Journal of the Indian Mathematical Society or the Mathematics Students, the periodicals published by the IMS. So Dr. Yadav is the recipient of this prize for the year 2020. His paper on some categories of Riemannian manifolds has been published in volume 86 of the Journal of the Indian Mathematical Society. So on behalf of the Indian Mathematical Society, we congratulate Dr. Yadav, and we would like to know his contributions in this paper. So with this brief introduction, I request Dr. Yadav to begin his presentation. Thank you.
Okay, thank you, sir. So I'll be continuing for 25 minutes, right, from here, and then 5 minutes for questions, right? Okay. So I will talk on some categories of Riemannian manifolds. First, table of content. Firstly, I'll talk on give introduction. Then I'll give some known categories of Riemannian manifolds. Then I'll give some new categories of Riemannian manifolds. Then new categories versus previously known categories. And then lastly, references. So, okay. So in mathematics, we study structures and relations between them. For example, continuous functions between topological spaces in topology, homomorphisms between groups in group theory, linear transformations between linear spaces in linear algebra, smooth functions between manifolds in the theory of smooth manifolds, and functors between categories in category theory are such relations. These relations are defined in such a way that they relate the structures of the objects within which they are defined. Such relations are called morphisms in category theory. Only well-known morphisms between two Riemannian manifolds are isometries and conformal maps. These morphisms are isomorphisms in their respective categories of Riemannian manifolds, but these morphisms are too restrictive. Other known interesting maps between Riemannian manifolds are conformal immersion, conformal submersion, isometric immersion, Riemannian maps, conformal Riemannian maps, etc. But classes of these maps between two Riemannian manifolds fail to be a morphism set in any category. Reason for this is that these classes are not closed under composition. Next, we will give some basic definitions. A function, a smooth function f from a Riemannian manifold M to another Riemannian manifold N is called conformal immersion if there exists a smooth function lambda f from M to the set of positive real numbers such that this equation is satisfied for all x, y in the tangent space of M at x for all x in M. If lambda fx equal to 1 for each x in M, then a conformal immersion f is said to be isometric immersion. If for some lambda f in R, lambda fx equal to lambda f for each x in M, so there is a typo here, and dimension M equal to dimension n, then a conformal immersion f is said to be a conformal map. A conformal map is called isometry if lambda fx equal to 1 for all x in M. Then we have an example, a function f from R to R2 defined by this is a conformal immersion. So this is straightforward verification, so one can easily verify it. We have next definition. We say that a smooth function f from M to N is a conformal submersion if there exists a linear subspace Hx in the tangent space of M at x, that is Txm, for each x in M, and a smooth function lambda f from M to R plus such that Bfx is surjective for each x in M. direct sum of hx and kernel of d of x is txm, and this relation is satisfied for each xy in hx, for each x in m. If hx is orthogonal to kernel of d of x for all x, then we say that f is horizontally conformal submersion. In addition, if lambda f x equal to 1, then horizontally conformal submersion f is said to be Riemannian submersion. Note that f is an isometry if it is isometric immersion as well as conformal submersion. Next, we have following example. So, if we define f from R4 to R2 by this, then f is a smooth function. It is clear, and we have its differential of f given by this. We can easily verify that this k, which is span of this, is a kernel of this d of a, and p, which is span of this, has this property that this k plus t equal to R4. So this direct sum is R4, and this f is conformal submersion with HA equal to P. And this lambda f a equal to 2 exponential 2a3 for all a in R4. Note that HA and kernel d of a are not orthogonal in this example. So that was a requirement for general conformal submersion. Next, we have another definition, a smooth function f from m to n. So here, spaces that will be talking about will be Riemannian manifolds. So a smooth function f from m to n is called Riemannian map if there exists a linear subspace Hx in Txm for each x such that Hx is orthogonal to kernel d of x, and this equation is satisfied for each x in M. We have an example of this. A function f from R2 to R2 given by this is a Riemannian map. So this also is a straightforward verification. Another definition we have, so this is given by Bayram Sahin. So previous definition was given by this Fisher. So this is given by the Riemannian maps were defined by Fisher, and this is given by Bayram Sahin. So it is defined as follows. A smooth function f from m to n is called conformal Riemannian map if there exists a linear subspace Hx in Txm for each x in M, and a smooth function lambda f from m to r plus such that Hx is orthogonal to kernel d of x, and this equation is satisfied. We have following example of this conformal Riemannian map. So based on the previous maps between Riemannian manifolds, we have following categories of Riemannian manifolds. So let Rm iso denotes the collection of all Riemannian manifolds together with mod iso Mn defined by this.